Solar energy. Solar energy is derived from the sun's radiation and can be converted into electricity or heat using photovoltaic, PV panels, or solar thermal systems, respectively. Solar energy is abundant, clean, and inexhaustible, making it a key renewable energy source. Solar power systems can be installed on rooftops, in solar farms, or in remote areas to provide electricity to homes, businesses, and communities. The widespread adoption of solar energy can reduce greenhouse gas emissions, decrease reliance on fossil fuels, and promote energy independence. 2. Wind energy. Wind energy is harnessed from the kinetic energy of wind using wind turbines. Wind turbines convert the wind's rotational energy into electricity through the use of blades connected to a generator. Wind power is a mature and rapidly growing renewable energy technology, with wind farms installed in various regions worldwide. Wind energy is clean, abundant, and cost-effective, with the potential to significantly reduce carbon emissions and mitigate climate change. 3. Hydroelectric energy. Hydroelectric energy is generated from the gravitational force of flowing water, such as rivers or streams, which drives turbines connected to generators. Hydroelectric power plants can vary in size, from small-scale run-of-river systems to large-scale dams and reservoirs. Hydroelectricity is a reliable and flexible renewable energy source, providing baseload power and storage capacity for electricity grids. However, large-scale hydroelectric projects can have environmental and social impacts, including habitat disruption, displacement of communities, and alteration of river ecosystems. 4. Geothermal energy. Geothermal energy is derived from heat stored beneath the Earth's surface in rocks and fluids. Geothermal power plants use steam or hot water extracted from geothermal reservoirs to drive turbines and generate electricity. Geothermal energy is reliable, constant, and environmentally friendly, with minimal greenhouse gas emissions and environmental footprint compared to fossil fuels. Geothermal power plants can be built in areas with high geothermal heat flow, such as volcanic regions and tectonic plate boundaries. 5. Biomass energy. Biomass energy is derived from organic materials such as wood, agricultural residues, and organic waste, which can be burned or converted into biogas, biofuels, or bioenergy through processes like fermentation and anaerobic digestion. Biomass energy is renewable and can serve as a low-carbon alternative to fossil fuels in transportation, heating, and electricity generation. However, sustainable biomass production and utilization practices are essential to mitigate environmental impacts such as deforestation, soil degradation, and air pollution. 6. Potential to mitigate climate change. Renewable energy sources have the potential to play a significant role in mitigating climate change by reducing greenhouse gas emissions, enhancing energy security, and promoting sustainable development. Transitioning to renewable energy technologies can help decarbonize the economy, limit global warming, and mitigate the adverse impacts of climate change on ecosystems, biodiversity, and human health. Policy support, technological innovation, investment incentives, and public awareness are critical for accelerating the deployment and adoption of renewable energy solutions worldwide. 7. Tidal energy. Tidal energy is generated from the gravitational forces of the moon and the sun, which cause the rise and fall of ocean tides. Tidal power systems use turbines or barrages to capture the kinetic energy of tidal currents and convert it into electricity. Tidal energy is predictable, reliable, and renewable, with the potential to provide a consistent source of clean power in coastal regions. However, tidal power technologies are still in the early stages of development and face challenges related to high capital costs, environmental impact, and limited deployment sites. 8. Wave energy. Wave energy is derived from the kinetic energy of ocean waves, which can be captured and converted into electricity using wave energy converters, WECs, deployed offshore. Wave energy is abundant, renewable, and has the potential to complement other renewable energy sources like wind and solar power. Wave energy technologies vary in design and complexity, including oscillating water columns, point absorbers, and attenuators. Despite its promising potential, wave energy development faces challenges such as device reliability, survivability in harsh marine environments, and grid integration. 9. Ocean thermal energy conversion, OTEC. Ocean thermal energy conversion, OTEC, is a renewable energy technology that harnesses the temperature difference between warm surface waters and cold deep waters in tropical oceans to generate electricity. OTEC systems use heat exchangers and turbines to convert thermal energy into mechanical power, which is then converted into electricity. OTEC is a clean and continuous source of renewable energy, with potential applications for island nations and coastal regions with access to deep ocean waters. However, OTEC faces technical and economic challenges, including high upfront costs, limited scalability, and environmental impacts on marine ecosystems. 10. Distributed energy systems. Distributed energy systems, DES, enable the generation, storage, and distribution of renewable energy at or near the point of consumption, reducing reliance on centralized power plants and grid infrastructure. DES technologies include rooftop solar panels, small-scale wind turbines, micro-hydro systems, and battery storage systems. Distributed energy resources, DERs, offer benefits such as increased energy resilience, grid stability, and energy independence, as well as opportunities for local economic development and community empowerment. 11. Renewable energy integration. Integrating renewable energy sources into existing energy systems requires addressing technical, regulatory, and economic challenges to ensure reliability, stability, and affordability of electricity supply. Strategies for renewable energy integration include grid modernization, energy storage, demand-side management, smart grid technologies, interconnection standards, and market incentives. Flexibility and adaptability are key principles for optimizing the integration of diverse renewable energy sources while meeting energy demand and climate goals. 12. In conclusion, exploring a diverse array of renewable energy sources and technologies offers opportunities to expand the global renewable energy portfolio, accelerate the transition to a low-carbon economy, and mitigate the impacts of climate change. Fostering curiosity, critical thinking, and innovation in renewable energy education can inspire the next generation of scientists, engineers, and policymakers to address the complex challenges of energy transition and sustainability. Thank you for watching. Please subscribe for more.